Hi Lena, welcome on board to this Q&A session of this particular topic, airspeeds. We'll be focusing on the question analysis. Further, we will be moving on to book reference, important concepts, formulae, and solutions regarding to the particular topic, airspeeds. Now let me switch on over to the blog consisting the GATE Aerospace materials. So here I am on the Edge of Aerospace blog and the GATE Aerospace tab. Here now moving on to the flight mechanics portion. Here we see the flight mechanics portion. And regarding the question analysis, here we can see that from this particular topic, equivalent calibrated and indicated airspeeds, there are about 3 1 marks asked in the years 2009, 16, and 19. Similarly, there are 3 2 marks which are asked in the year 2008, 18, and 20. So this makes this a pretty important topic. Now, switching on over to the book reference. For getting a deep knowledge about this particular topic, you can go through the Introduction to Flight, J.D. Anderson. And the particular section which deals with this is measurements of airspeed, the 4.11, and the page numbers are mentioned over here. Regarding the important concepts, you need to know the Bernoulli's equation. It's nothing but the momentum equation applied to the aerodynamic or aerospace application. So next, of the three particular airspeeds, or I can say four particular airspeeds, including the true airspeed. So of these four airspeeds, the major airspeeds or the major portion of question which was focused was on true and equivalent airspeeds. So these formulas are pretty much important. Now, regarding this topic, you need to know the basic definitions of these four airspeeds, which you need to remember in a simple manner. So let me provide an insight. Indicated airspeed is nothing but the direct airspeed which is shown on the ASI or airspeed indicator. Calibrated airspeed is basically the airspeed which is corrected for or calibrated for instrument error and system position error. So here, equivalent airspeed is nothing but the airspeed which the aircraft need to fly to replicate the same level of airspeed at some particular altitude. We'll be focusing a detailed definition in the further portion of this video. And regarding the true airspeed is nothing but the actual airspeed which the aircraft is flying, and it takes in account the actual density at that particular altitude. Now here we are further moving on to the formulae portion of it. In this particular topic, there are two important formulas. That is a formula for true airspeed and equivalent airspeed. Now let's get to see them one by one. So here, true airspeed. Regarding true airspeed, velocity of true airspeed can be found out by square root of 2 times P naught. P naught is the stagnation pressure, and P is the static pressure. That is twice the amount of pressure difference between the stagnation and static pressure divided by density. So this density rho is the density at that particular altitude which it is flying. So here we can see this is basically derived from Bernoulli's equation, that is half rho v square p naught p plus half rho v square is equal to p naught. So by rearranging this, we will obtain the VTAS. So this is how we basically derive it. We have discussed about this in the corresponding lecture. Now getting to the equivalent airspeed. The formula for equivalent airspeed is basically derived from true airspeed, or ideally it can be written as square root of 2 times Q is the dynamic pressure divided by the density at sea level, which is 1.225 kilogram per meter cube. So this is a standard quantity. And other important formula is EAS is equal to TAS times square root of rho by rho s. Rho s stands for sea level density, and Q is nothing but the dynamic pressure, which is half rho v square. Now, before getting to solve questions, we need to know one particular important usage or material. Here we have GATE scientific calculator, which you need to get used to, because in GATE aerospace examination or GATE examination, you will not be allowed to carry any other kind of calculators. So here you need to get used to this kind of calculator. And one other point to about this is that you cannot use your keypad, so you can only use this visual calculator by the help of mouse. So if you need to click any number, you need to click by this particular mouse, and do get used to these functions, and get ready with having some comfort with this, because this may slow you down in the examination. Now let's get solving. So here, now we are going to solve the topic wise solution. Here we have a first question from GATE 2009, and it is in 1 mark from this topic, equivalent calibrated and indicated airspeed. Now, getting to read this question, the question mentions that the relation between an airplane's true airspeed and equivalent airspeed in terms of density ratio, where P naught, they have provided the density ratio, that is sigma equal to density rho by rho naught, where rho naught is the air density at sea level and rho is the air density at uh, that particular altitude at which aircraft is flying. And they are basically asking the relation between airplanes true airspeed and equivalent airspeed. They are asking a relationship between velocity VTA's true airspeed and equivalent airspeed in terms of density ratio. They have defined the density ratio, that is ratio of density at the particular altitude and ratio of density at that sea level. So here now, providing the relation, um, here we need to know that equivalent airspeed is a speed with which the aircraft needs to fly at sea level to duplicate the actual dynamic pressure at a given altitude. So based on this, it basically relates the value at which the aircraft needs to fly at sea level to replicate the similar dynamic pressure at true airspeed or some particular altitude. So this is basically dealing with the dynamic pressure. So when we relate the dynamic pressure of true airspeed and equivalent airspeed, or also known as velocity, here the difference between velocity and speed is that speed is an scalar quantity and velocity is a vector quantity where it has speed plus direction. So here, relating the dynamic pressure terms, we can easily obtain the ratio. So we are keeping the VAS this side and rearranging the terms VTAS. So here we can see the half and half get cancelled, and we can see that rho by rho naught is obtained. So we will be obtaining similar kind of relation. So by the question itself, we know that this relation is the density ratio, which is sigma. So this VEAS by VTS can be written as square root of sigma. Let's check the answer. So based on this, option C must be the right answer. Let's check the answer key. So as answer C, VEAS by VTS is equal to square root of sigma is the right answer. Getting to the second 1 mark question from GATE 2016, they are basically asking the indicated airspeed is used by a pilot during. So they are asking the purpose of an IAS or indicated airspeed. The options are takeoff, setting the engine RPM, navigation, setting the elevator angle. So solving this question, during takeoff, we know that the density variation isn't significant because the altitude variation is not high during takeoff. So therefore, TAS and EAS can be neglected. That means TAS and EAS are basically dependent on density at some particular altitude. As during takeoff, the height is within 50 meters or something, the density variation isn't significant. That is the density from uh, 1.225 kilogram per meter cube is the density at sea level. So with 50 meters change, the density variation will be in the third term or something. So based on this, TAs and EAs can be neglected, and simplest airspeed reading is preferred during the takeoff. Thus, indicated airspeed is the simplest airspeed, which is directly shown by the aircraft speed indicator. So this might be used for takeoff. It is indicated airspeed. Let's see the other purpose of the other airspeeds too. So here we can see the indicated airspeed can be used for takeoff, as it is a direct reading shown by airspeed indicator. Regarding the calibrated airspeed, it takes in account the indicated airspeed and then it calibrates the other quantities, that as installation error and something else. So This needs to some care, and this is basically used for navigation. And today's aircrafts use GPS instead. And true airspeed, similar case, it varies with density. So at sea level, we can say it might be same, and it might not vary. And here, equivalent airspeed is basically used for structural analysis as it provides the same condition at sea level that needs to be or attained at some particular altitude. So this is basically used for structural analysis as it is a direct function of incompressible dynamic pressure. So based on this, indicated airspeed can be the right answer for the purpose of takeoff. So let's see, say takeoff. Now regarding other three options, navigation can be the airspeed which deals with navigation is CAS or TAS. So it is not IAS or indicated airspeed. So for setting the RPM and elevator angle, we need the accurate airspeed. Particularly for elevator angle, we need the calibrated or the airspeed corrected for installation or position error. So for this, we may need the calibrated airspeed. Similar case is with the setting the engine RPM. So we are left off with takeoff. Let's check the answer key. So yes, takeoff is the right answer. So here is another one mark question from GATE 2019. And here we can see an airplane is in steady level flight with true airspeed 50 meter per second. The ambient air density uh, pressure at that flight altitude is they have provided the density and pressure at that particular altitude respectively. At sea level conditions, air density is 1.225 kilogram per meter cube and ambient pressure is 1.01 into 10 to the power 5 Newton per meter square or pascals. The equivalent or indicated airspeed of the airplane is in meters per second. They are asking in two decimal places, round off. So here, writing down the given, they have provided the true airspeed, the density at the pressure at that particular altitude, and sea level density and pressure. So we know the formula. They have asked the equivalent and or indicated airspeed. Now we have the formula for equivalent airspeed. We know that VEAS is equal to VTAS times square root of density ratio or rho by rho naught. Now substituting the values, we have VTAS that is 50 and rho is already provided, and similarly taking the sea level condition, we will obtain the answer as 43.09 meter per second. And in this particular answer, we need to focus that they have asked rounding off to two decimal places. So you need to consider these two decimal places because it may deal with the answer. So checking the answer, yes, we are good to go if the answer remains between 43.05 to 43.15. And here we see the answer is 43.09, which in particular remains within this range. So it is a correct answer. So as I said, this the rounding off to two decimal points. Here we can see the answer ranges starts from 05 to 15. So if you basically write 43 and leave off the other part, you may get it wrong. So do show some focus on it. Getting to the 2 marks, here we have a 2 mark question from GATE 2008, and the question mentions an aircraft is cruising at true airspeed of 100 meter per second under international standard atmosphere conditions. So at an altitude at which the density of free stream is 0.526 kilogram per meter cube, what will be the equivalent airspeed? So they are basically asking the equivalent airspeed. It is same as the previous question. Now, writing down the given, they have provided the VTAs and density at that particular altitude. Similarly, they have mentioned international standard atmosphere conditions at sea level. So we can consider the standard atmosphere conditions, that is rho naught is equal to 1.225 kilogram per meter cube, and P naught is 1 atmosphere, which is also 1.01325 into 10 to the power 5 Newton per meter square, or we can write it as bar. So this whole term can be written as bar instead. Um, and here T naught is the temperature at sea level, which is 88.16. We know that the formula for VEAS is VTAS times the density ratio, square root of density ratio. Now substituting in the values, we can obtain the answer as 65.53 meter per second. Now here we can see it is multiple choice question. So we can write down the answer. The option which matches with is 65.53 is 65.5. So the answer must be A. Let's check the answer key. So as the answer key mentions that A is the right answer, 65.5 meter per second. Now let's get to the other question, the fifth question. So here we have a 2 mark question from GATE 2019. Or, I think this question is from 18 maybe. So here, an aircraft with a gross weight of 2000 kilogram has speed of 130 meter per second at sea level, where the conditions are 1 atmosphere and 288 Kelvin and 1.23 kilogram per meter cube. The speed in meter per second required by the aircraft at an altitude of 9000 meter, where the conditions are pressure 0.31 atmosphere, temperature 230 Kelvin, and density 0.47 kilogram per meter cube. So to maintain a steady level flight, what must be the speed that the aircraft needs to fly? So here they have mentioned that the answer must be accurate to two decimal points. So we need to follow the similar condition from the previous question. Now writing down the given, they have provided the weight. As they have mentioned the speed at sea level, it is VEAS or equivalent airspeed. It is 130 meter per second, and pressure, temperature, and density at sea level are already provided. And they are asking the speed at which the aircraft needs to cruise for a steady level flight at an particular altitude of h is equal to 9000 meter, density 0.47 kilogram per meter cube, and this particular pressure and temperature. Now, from the formula, we know that VAEAS or equivalent airspeed is VTAS or true airspeed times the square root of density ratio. Now, getting back the VTAS, we can write the relation as such. And for finding out the true airspeed, so true airspeed is the airspeed at that particular altitude. We can rearrange this equation. So this will go to the right side, and this whole portion will go to the left side into the denominator. Now VTAS can be written as VEAS by square root of rho by rho naught. Now substituting in the values, we know the velocity at sea level, which is also the equivalent airspeed. So 130 meter per second divided by 0.47 square root of 0.47 divided by 1.225. We will obtain the answer as 210 meter per second. Now checking in the answer key, the answer must range between 2009 209 to 211. So we are good to go as the answer range lies between this. So getting to the next question here, this is a 2 mark question from 2020, and the question reads out as a petard tube mounted on the wingtip of an airplane flying at an altitude of 3 km measures a pressure of 0.72 bar and outside air temperature is 268.66 Kelvin. Take the sea level conditions as pressure 1 bar, temperature 288.16 Kelvin, and density 1.225 kilogram per meter cube. Now they have provided the acceleration due to gravity is 9.8 meter per second, and the gas constant is 287 joule per kg Kelvin. And assuming the standard atmosphere conditions, the equivalent airspeed of this airplane is. So they are basically asking in for the equivalent airspeed, that is VEAS. So the based on the conditions provided, let's check out the conditions and write out the given. So here we can see they have mentioned a pitot tube. So pitot tube is basically used to measure the stagnation pressure P naught, not the static pressure. If it is mentioned pitot static tube, then it measures both the pressure difference. That is, the static tube measures the static pressure P, and pitot tube measures the stagnation pressure P naught, and the difference is provided as the output of pitot static tube. So here, as they have mentioned a pitot tube, the pressure measured by it is P naught or stagnation pressure. So it is written over here, and the altitude is provided as 3 kilometers. So in meters, it is 3000 meters altitude, and density it is provided as 0.47 kilogram. So this is basically from the previous question. So you can strike out the density. So this is not in this question. Sorry. And here the temperature is provided as 268.66 Kelvin. Now they have also provided the sea level conditions, pressure at sea level. So not to confuse the stagnation conditions and sea level conditions, I have written the sea level conditions as PSL, and P naught means the stagnation conditions. So here 1.01 bar, which is 1.01 times 10 to the power 5 Newton per meter square. This is just the alternate representation of it. And temperature at sea level is 288.16 Kelvin as written over here. And density at sea level is provided 1.225 kilogram per meter cube. And they have also provided the acceleration due to gravity g and gas constant r 287 joule per kg Kelvin. Now here for finding out VTEAs, we basically use the formula VTEAs times the square root of density ratio. But here there is no mention about the VTAs or true airspeed, so we cannot use that formula. Instead, we will be finding it out by other way. So here they have provided the stagnation temperature, stagnation pressure at this particular altitude 3 kilometers. So if we somehow find out the static pressure P, we can easily derive the VTAs. So if we derive the VTAs, we can write out the VAs from the previous formula. So now let me first find the static pressure at that particular altitude. So from the first lecture, or in particular the topic atmosphere and altitude, we can write the relation between the ratio of pressure at some particular altitude to sea level with temperature at that particular altitude to sea level as this. So this is from the first lecture, atmosphere and altitude. So now when I write this particular relation, P by PSL is equal to T by TSL power minus G by AR. So this A is the lapse rate, which is minus 0.0065 for the first gradient layer, or you can also find out the lapse rate as A is equal to the temperature difference. So here they have mentioned the temperature at that particular altitude at as 268 point some values, so 268.66 minus the sea level condition temperature is 288.16, 288.16, so divided by the height, that is nothing but this relation is nothing but A is equal to dt by dh. So if you derive this, you will be basically obtaining the value 0.0 minus 0.0065 Kelvin per meter, which means the temperature decreases with this particular ratio. So it's better if you remember that. Now getting to solve this. Now when we substitute the sea level pressure, which is already provided in bar, and substitute the value of T at that particular altitude and the sea level temperature, which is already provided, and writing down the value of gravity, acceleration due to gravity 9.8, and A lapse rate, and R this gas constant, uh, we can obtain the value as the static pressure is 0.699. That is, this is taken to the right side for multiplication, and this can be in a round off value can be written as 0.70 bar. Now we have obtained the static pressure. So if we have the static pressure, we know the from the formula of true airspeed, which is square root of 2 times the pressure difference by the density at that particular altitude. So we have the stagnation temperature 0.72 bar already measured by the pitot tube at that particular altitude 3 kilometers, and we have found out the static pressure. Normally, when the term pressure is mentioned, it means static pressure. So, in specific, if it is mentioned the velocity is decelerated to isentropically to zero, then it means stagnation pressure. Or they will particularly mention that it is stagnation pressure. So here, when we substitute in the values, the P is the P over here. Uh, Here we can see the square root of 2 times 0.72 is the value measured over here times 10 to the power 5 minus 0.70 times 10 to the power 5. So this is in pascals. So we have substituted some value density. So we know that density at that particular altitude isn't mentioned over here. They have provided the pressure and temperature, but they haven't provided the density. So for finding the density, you can use the equation of state, that is P is equal to rho RT, and rearranging you will obtain the relation for density. Density is equal to P by RT, and if you substitute the values, the static pressure 0.7 2 times 10 to the power 5 divided by RT, you will obtain the value 0.9338. Or you can always obtain this particular value from the basic relation from atmosphere and altitude. The relation must be like for rho by rho sea level, the relation is same minus 1. So this is the relation. You can always check in with the formula for this particular topic. You can find out the density either way, and here you can also substitute the value 0.70 instead. There may not be much difference. So here we can substitute the values in this particular equation. So we will be obtaining the VTA's true airspeed at as 65.45 meter per second. So okay, we have obtained the VTAs, but the question asks the equivalent airspeed VEAs. Now getting to solve the VEAs, we can see VEA's formula as VTAs times the square root of density ratio rho by rho naught. Now we have already derived the VTA's value. So when we substitute it over here and substitute the value for density which we found out over here, and the density at sea level, we can obtain the answer as 57.14 meter per second. Now when we check out with the answer key, we are good to go if the answer ranges between 57.10 to 60. So here we obtain the answer as 57.14, which pretty much lies between this range. So our answer is the correct answer. And do mention or do focus that the answer has to be round off to two decimal places. Please do not miss this. So you may get the answer wrong, or your answer may not be provided marks if you do such way. So that's it for this session. Let's crack GATE Aerospace. Thank you.